You've unplugged a vacuum cleaner 100 times, that little blue spark that snaps between the plug and the outlet. You've seen it. Maybe you even flinched the first time. But have you ever actually understood it? Have you ever asked why it happens when you break the connection, not when you make it? Have you ever wondered why it's bright with some devices and invisible with others? Most people haven't. They just accept it. Electricity does that sometimes. Static spark, old outlet. But when you dig into what's actually happening in that instant, the physics of that tiny flash, you discover something that changes how you see every electrical device in your home. You discover that electromagnetic fields don't die quietly. They resist annihilation, and that resistance creates a phenomenon identical to lightning. That spark isn't a bug. It's a feature of reality itself. Let me show you. The standard explanation is that it's arc discharge, or residual current finding a path. You might have seen diagrams in a textbook showing electrons jumping across a gap. It's not wrong exactly, but it's missing the point entirely, because if it were just leftover electrons draining away, the spark would be bigger when you first plug something in, when you're suddenly flooding the circuit with current. But that's not what happens. The spark appears when you break the circuit, when you're stopping the flow. But once you see what's really happening, once you understand what an electric current actually creates around itself, you realize that unplugging isn't just stopping electricity. It's destroying something that's been building the entire time the device was running. There's something here that nobody talks about, something about electromagnetic fields and their absolute refusal to simply vanish. And it connects to transformers, to car engines, to lightning itself in ways that should make you see electricity completely differently. Let me show you what I mean. Start with something simple, something happening right now. Start with something simple. Right now, if there's anything electrical running near you, a fan, a phone charger, a lamp, there's an invisible field surrounding the wires. You can't see it, you can't feel it, but it's there. It's called a magnetic field, and every single wire carrying electric current creates one, not as a side effect, not as waste. The magnetic field is inseparable from the current itself. Moving charges, electrons flowing through copper, generate magnetism the way a moving object generates a wake in water. This has been measured, proven. Hans Christian Ørsted discovered it accidentally in 1820 during a lecture demonstration. He brought a compass near a current-carrying wire and watched the needle deflect. The room went silent. Electricity and magnetism weren't separate forces. They were two faces of the same phenomenon. Now here's what matters. That magnetic field isn't just sitting there doing nothing. It's storing energy, real, measurable energy. The stronger the current, the stronger the field. The more wire you coil together, the more energy gets locked into that invisible magnetic structure around it. Motors have lots of coiled wire. So do vacuum cleaners, fans, power tools. When they're running, they're not just consuming electricity. They're building a magnetic field around their coils. Energy from the wall outlet is being stored, not in the device itself, but in the space around the wires. Stop and think about that for a second. Energy stored in empty space, in the field itself. Now what happens when you yank the plug out? The current stops instantly. And when the current stops, the magnetic field that depends on that current has to collapse. It has no choice. No current, no field. But that's just the surface, because if that magnetic field was storing energy, real energy measurable in joules, then where does that energy go when the field collapses? Energy doesn't just vanish. That's not how physics works. So when you break the circuit, you're not just stopping the flow of electricity. You're forcing a magnetic field full of stored energy to disappear in a fraction of a second. And that field, it doesn't go quietly. Here's what happens in that instant. When you break the circuit, the current tries to stop. But the magnetic field around the wire, the field that's been storing energy, collapses. And a collapsing magnetic field does something remarkable. It induces a voltage in the wire. This is called electromagnetic induction. Michael Faraday figured it out in 1831. Change a magnetic field near a conductor, and you create voltage in that conductor. Move a magnet through a coil of wire, voltage appears. Spin a coil inside a magnetic field, you get a generator. The entire electrical grid runs on this principle. But here's the thing, it works in reverse too. When you break a circuit, you're not just stopping current. You're changing the magnetic field from maximum to zero in a fraction of a second. And that collapsing field induces a voltage in the wire, a voltage that tries to keep the current flowing. The field resists its own destruction. It fights back by creating a voltage spike in the exact direction needed to maintain the current that's disappearing. Think about what that means. The act of turning electricity off creates a burst of voltage trying to keep it on. This voltage spike has a name, back-EMF, electromotive force. The back part means it opposes the change you're trying to make. You pull the plug. The collapsing magnetic field says, not so fast, and generates a voltage pulse trying to sustain itself. Engineers deal with this constantly. Every relay, every switch, every circuit breaker that controls inductive loads, motors, transformers, solenoids, has to handle back EMF. Ignore it, and it will destroy your components. But wait, that raises another question. If the circuit is broken, if the plug is physically separated from the outlet, how does that voltage spike go anywhere? The wire isn't connected anymore. There's a gap. Air. How does electricity cross air? Here's where it gets strange. You've been told that air is an insulator, that electricity doesn't flow through air under normal circumstances. And that's mostly true. Air molecules are stable. They don't conduct. But, and here's the thing that should bother you, air can be made to conduct. You just need enough voltage. Under normal conditions, the 120 volts from your wall outlet can't jump across an air gap. The voltage isn't high enough to break down the insulating properties of air. But when that magnetic field collapses, it doesn't generate 120 volts. It can generate hundreds or even thousands of volts in a millisecond. The exact voltage depends on how fast the field collapses and how much energy was stored in it. Motors with large coils can create massive voltage spikes. The faster you break the connection, the faster the field collapses, the higher the voltage. And when that voltage gets high enough, something remarkable happens to the air. The electric field becomes so intense that it rips electrons off air molecules. It ionizes them. Neutral nitrogen and oxygen atoms become charged particles, a plasma, and plasma conducts electricity. Think about what that means. The collapsing magnetic field generates such high voltage that it forces the air to become conductive. It creates a path for current where none existed. That's your spark, that blue-white flash. That's not just electricity jumping. That's ionized air. That's a plasma channel forming in the gap between the plug and the outlet, allowing the dying magnetic field to dump its energy one last time. The air is literally being ripped apart and turned into the fourth state of matter for a fraction of a second. This is the same physics that creates lightning, a voltage difference so extreme that it ionizes a path through kilometers of atmosphere. Your spark is miniature lightning. Same principle, same plasma channel, just smaller. This has been measured. We know the breakdown voltage of air, roughly 3,000 volts per millimeter at sea level. That spark you see jumping a 2 millimeter gap, that's a 6,000 volt spike from a 120 volt circuit. The collapsing magnetic field created a 50 times voltage multiplication in the instant you pulled the plug. But that's still not the full story. If this voltage spike is so powerful, why doesn't it destroy the device? Why doesn't it arc back through the electronics and fry everything? Now we're getting to the core. This is where most explanations stop, but we're going deeper. The magnetic field doesn't just store energy, it stores energy over time. The technical term is inductance, measured in henries. It's a measure of how much magnetic field a coil of wire can build up for a given current. High inductance means the field builds slowly and collapses slowly. Low inductance means it changes quickly. But here's what happens when you force a high inductance field to collapse instantly by breaking the circuit. All that energy has to go somewhere in a vanishingly small amount of time. Energy divided by time is power. Compress the same energy into a shorter time window, and the power spikes enormously. That's why the spark happens at the plug, not inside the device. The plug gap, that physical separation between metal contacts, is where the circuit breaks. That's where the magnetic field is forced to collapse fastest. That's where the voltage concentrates. The field essentially throws all its stored energy at that gap in a last desperate attempt to keep current flowing. And if the voltage gets high enough to ionize the air, it succeeds for a microsecond. Current flows through plasma until the energy is exhausted. This should break your brain a little bit. The magnetic field doesn't want to collapse. That's anthropomorphizing, but it's functionally accurate. The mathematics of inductance describe a system that resists changes to current. When you force that change anyway, the field generates whatever voltage is necessary to oppose you. Pull a plug slowly, and you give the field time to collapse gradually. The voltage spike is smaller, maybe no visible spark. Yank it fast, and you force instantaneous collapse. The voltage spike can reach thousands of volts. Guaranteed spark. You control the voltage spike with your hand speed. And here's what that means for everything you thought you understood about electricity. Here's what nobody tells you when they teach you to unplug things safely. Every electrical device with a coil, every motor, every transformer, every relay is a spring made of magnetic field. When it's running, you're winding that spring. When you unplug it, you're releasing that spring all at once. The spark is the spring snapping back in your normal experience of the world. Electricity is something you control. Flip a switch, it flows. Flip it again, it stops. Pull a plug, you break the circuit. End of story. The power stops because you said so. You're in charge. Except that's backwards. You don't control when the current stops. The magnetic field does. When you yank that plug, you're not ending the electrical flow. You're triggering a rebellion. The magnetic field that has been silently building the entire time the device was running suddenly has a problem. It can't exist without the current that created it, but it's full of energy, real energy, and that energy cannot simply vanish, so it doesn't. It induces a voltage spike so violent that it forces current to keep flowing, even through air, even through the gap you just created. It ionizes the atmosphere between the contacts, creates a plasma bridge, and dumps its energy through that momentary path. You pulled the plug to stop the electricity. The electricity said no. Let me prove it to you. Look at the spark next time you unplug a vacuum cleaner. That blue-white flash lasts maybe 10 milliseconds. In that 10 milliseconds, the collapsing magnetic field generates a voltage spike potentially 50 times higher than the wall outlet provides. It superheats a channel of air to temperatures exceeding 3,000 degrees Fahrenheit, hotter than the surface of some stars. It creates plasma where there was only atmosphere. This isn't speculation. This is measured. This is why arc flash protection is a mandatory safety standard in industrial electrical work. This is why relay contacts are made of special alloys designed to withstand plasma erosion. This is why snubber circuits exist in electronics, specifically to absorb the violence of collapsing magnetic fields. Think about what this means. Every motor in your house is a loaded weapon, not dangerous in the explosive sense, but loaded with magnetic energy, waiting to discharge the moment you break its circuit. That spark between your fingers isn't leftover electricity draining away. It's the magnetic field's revenge, the same field that was invisibly, silently storing energy for as long as the device was running, the same field that exists in the space around the wire, not inside it. The same field that refuses to collapse without a fight. Every time you unplug something with a motor, you witness a tiny thunderstorm, the same physics that creates lightning happening between your fingertips. That's not a metaphor. That's not poetry. That's the actual structure of electromagnetic reality. This isn't a bug in the system. This isn't a failure. This is what inductance does. This is what magnetic fields are. And once you see this, you realize unplugging a vacuum cleaner isn't isolated. It connects to everything. Now here's what people miss when they learn just about sparks and unplugging. This phenomenon isn't isolated. It's not a quirk of wall outlets. It's one of the most fundamental principles in electrical engineering, and it's everywhere. The same collapsing magnetic field that creates a spark when you unplug a vacuum cleaner also fires the spark plugs in your car. The ignition coil builds a magnetic field, then collapses it deliberately to generate 40,000 volts from a 12-volt battery. That voltage spike creates the spark that ignites the fuel. Every combustion engine on Earth runs on controlled inductive kick. Powers every transformer on the planet. The entire electrical grid, every power line, every wall adapter, every phone charger uses changing magnetic fields to transfer energy between coils. No moving parts, just fields building and collapsing millions of times per second. Makes arc welding possible. Welders deliberately exploit the plasma-forming power of collapsing fields. They strike an arc and sustain it. A continuous controlled spark hot enough to melt steel. Creates the flash in a camera. The flash circuit charges a coil, then releases that magnetic energy in a single violent burst through a xenon tube. Same principle, same collapsing field. Causes lightning. Charge separation in clouds creates enormous electromagnetic stress. When it releases, the voltage ionizes a path through kilometers of atmosphere. That plasma channel is exactly what forms between your plug and outlet, just scaled up by a factor of 1 billion. What looks like many different phenomena is actually one principle manifesting over and over. Magnetic fields store energy. Break the circuit that sustains them, and they will generate whatever voltage is necessary to release that energy. Slowly, if you let them. Violently, if you don't. This is called Lenz's law. Heinrich Lenz formalized it in 1834. The induced voltage always opposes the change in current. Always, without exception. You're not separate from this. Right now, electrical signals are traveling through neurons in your brain. Those signals create tiny magnetic fields. When those signals stop, those fields collapse, and they generate back-EMF too. The physics of your thoughts follows the same rules as the spark at your outlet, the same law, the same principle. From lightning to brain function to your vacuum cleaner, that's not mysterious. That's not complicated. That's magnificent. That's what electromagnetism actually is. So when you unplug something tomorrow, remember what you're actually witnessing. So why does unplugging something create a spark? Not because of static electricity, not because something's wrong with your outlet, not because of leftover charge draining away. It sparks because you just destroyed a magnetic field, a field that was silently storing energy in the space around the wire, a field that cannot vanish without releasing that energy, a field that, in its final microsecond of existence, generates a voltage spike violent enough to ionize air, create plasma, and force current through a gap you thought you'd broken. The spark is the field's last breath, a burst of physics so fundamental it connects vacuum cleaners to lightning, phone chargers to car engines, wall outlets to the neurons firing in your brain right now. But understanding this isn't just about sparks. It's about what kind of universe we live in. 200 years ago, electricity and magnetism seemed like separate mysteries. Then Ørsted noticed a compass needle twitch. Faraday wound coils and watched voltages appear from nowhere. Maxwell wrote 4 equations and unified light, electricity, and magnetism into one framework. Tesla saw that framework and built the modern world. We went from sparks are mysterious to we understand this so precisely we can engineer it. That's not a small thing. The fact that magnetic fields follow predictable laws. The fact that we can calculate the exact voltage spike from a collapsing inductance. The fact that the same equations describe a spark at your outlet and a lightning bolt splitting the sky. That's the triumph of human intelligence. The universe didn't have to be comprehensible, but it is, and we figured it out. That spark isn't annoying, it isn't dangerous, it isn't random. It's a window into the fundamental structure of reality, a reminder that electromagnetism, the force holding your atoms together, carrying signals through your nerves, lighting your room right now, follows laws so elegant we can hold them in our minds. That's what the spark really is. Not leftover electricity, the revenge of the field, not a glitch, not an accident, truth. If this journey into the physics of a spark changed how you see that little flash at your outlet, subscribe and share it with someone who still thinks it's just static electricity. What other everyday phenomena do you walk past without understanding? What else have you accepted without ever really asking why? Tell me in the comments, because I promise you, whatever you name, there's something deeper hiding underneath. There always is.